Hello, today we learn more about NP chart and C chart. So you know that we use P chart for monitoring process fraction nonconforming using sample fraction nonconforming. Now another chart for attribute variables when we have binary actually output as 0 and 1 or conforming nonconforming is NP chart, which is based on monitoring the process using the number of non-conforming items in a sample defined by D. Because it's coming from a binomial process, the mean is NP and the variance is NP times 1 minus P. If P is known, then I can easily find UCL, CL, and LCL. So there is a relationship between NP chart control limits and P chart. If you multiply the control limits of P chart by N, you get the control limits for NP chart. And for that reason, there is no difference between performance of NP and P chart. However, NP chart is easier to understand because it's not percentage, especially when you are working in basically on the floor. Maybe it's easier to communicate with some of the operators using NP chart rather than P chart. What if P is not known? In this case, we need to estimate P using this equation. So is the summation of all bad parts divided by the summation of sample that we have. So if you remember, let's say we have m samples, and in each sample we have, let's say n is 100, so we are inspecting 100 parts, and we record the number of non-conforming items. Here, let's say is 20, 10, blah, blah, blah. And then here we can find P bar as the summation of di divided by the total number of sample that we have, which is m times n when n is fixed. So that summation of ni can be replaced by m times n, number of sample times sample size. After finding P bar, we can just replace P0 with this P bar and get LCL, UCL, and CL. So here is one example. We inspect transmission cases each time 16 times in a day, and each time we inspected 100 of them. Okay, and we want to use this information to find the trial control limits. We are in phase 1 for NP chart. So here is the inspection result. As you can see, the first one out of 100, I have 5 non-conforming. So we have the summation as 88. 88 divided by 100 times 16. 100 is sample size and 16 is m. Then I get P bar as 0.05. So based on the equation I have, I can calculate UCL and LCL, and the equations are, if you remember, NP bar plus minus K, which is usually 3, NP times 1 minus P bar. So P bar, N is 100, K is 3, and P bar is calculated here, which is 0.055. Then we can get LCL and UCL, and as you can see here, this is LCL, this is UCL, and you plot the I values here. It seems that one point is out of control. We find the root cause, we take corrective action, we remove this point, we recalculate. So remove this point, we recalculate P bar. As you can see, now we have only 15 because we removed one of them. This is the new P bar is smaller, so that's why the revised control limit is tighter. This is the revised control limit for LCL and UCL. After that, you can see all the remaining points are in control. Therefore, we are all set, and we can. These are the baseline limits, and we can move to phase 2. NP chart and P chart have the same performance in terms of detecting out of control situations. And we prefer to use NP chart. So when we should use P chart? When we have variable sample size. So by that I mean every time that I go to collect some parts, the number of parts that we're collecting is different. So once is 100, another time is 50, the other time is 110. Maybe depending on the production rate, the sample size could be different. In that case, we do not use NP chart. And the main reason for that is NP chart center line. If I go back to this slide, you can see that the center line of NP chart depends on N. However, the center line of P chart doesn't depend on N. That's why we prefer to have constant center line and we use p-chart when the sample size is variable. So when the sample size is variable, how we can have p-chart implemented? What we do, we use variable control limits. The control limits, as you can see here, depends on n. Center line doesn't. So the center line is the same, is p bar, which is the summation total number of defectives and total number of observations. Is p bar, it's the center line. However, the control limits depends on n, and since n is variable, therefore your control limit would be variable, and as you can see, it's like a step control limit depending on n. When n increases, the control limits are tighter. When n is small, the control limit is wider. Okay, here is one example. As you can see, we have different sample sizes. So 25 is m, but the sample sizes are different, 100, 80, 80, and so on and so forth. And out of this 100, I have 12, so I can calculate pi, which is this di divided by n, 0.12. For this guy is 88, 8 divided by 80, which is 0.1, and I do this calculation for all of them. Then for each sample, I need to find basically the UCL and LCL differently. But first of all, I need to find P bar, which is summation of all defective items, or DI, divided by summation of all inspected parts. So it's 234 divided by 2450, and in this case is 0.096. So I have our basically P bar, which is the center line, and I use the equation that we had here for finding control limits for each sample separately. Okay, so for sample 1, this is the LCL and UCL for sample 2, and so on and so forth. And as you can see, if the LCL is negative, we set it as 0. And here is basically the plotted points, which are the PI values, and all of them are in control except for one of them. We can say, if there is no assignable cause for that, we can say it's a false alarm, and we can just ignore it and or leave it in the data set. We do not need to do recalculation. But if there is some assignable cause associated with that, we need to take corrective actions and remove this data point and redo the calculations. So redoing the calculation means we need to calculate P bar again, and based on new P bar, we need to recalculate all the control limits again. Now, we are done with P and NP control chart. We want to see how we can use Minitab to construct P and NP chart. So we have one example, and as you can see, we have 30 samples, and each sample contains 100 parts. So what I do, I go to stat, control chart, attribute charts, and I want to plot NP chart first. Select NP chart. What is the variable that I have is here. What is the subgroup size? In that case is 100. And then I push OK button. So as you can see, I have 2 out of control points. Doing corrective action, finding assignable cause, now we need to remove them. So what are those 2 points? In the session, I can see that these 2 points are 15 and 23. So I go to NP chart options, estimate, and I say remove these 2 points, 15 space 23. So these 2 are removed. And as you can see, after plotting that, these are 2 points removed, 15 and 23, and this is the limit. I don't see any other points out of the limit. And as you can see, this is only 15 and 23. There is no new point out of the limit. It's a finalized control chart. I can use it for phase 2. As I said, for phase 2, what we need to do, if we want to have a phase 2, first of all, for the phase 1, we need to store the proportions, estimated proportions. We do that, we get that estimated proportion, and then when we want to do phase 2, we go to NP chart options, and in the proportion, the proportion that we estimated in phase 1. So what it does, it doesn't use the phase 2 data to estimate proportion. It just uses this value to construct the control limits. Very similar to what we said for the X bar and R chart. But one point here is why we are using two charts for X bar for the variables, but only one chart for attributes, or we use only NP or C. For variable, we use X bar R. It's always paired chart. And the reason was because we want to monitor both mean and variance. So one chart for mean, one chart for variance. The reason why we are not using two charts for attribute is that both mean and variance of the process are function of P. If you look at the formulation that we have, both mean and variance depend on P. That's why by monitoring P, we can monitor both of them. Now let's see a variable sample size case here. As you can see, we have in one column different n, and in one column we have different the corresponding basically non-conforming items. So I go to stat, control charts, attribute, and I use P chart because it's variable control limit. So what is that variable? Is di. What is the subgroup size? We don't have constant subgroup size, but subgroup size is in C2. So I use that, press OK. And as you can see, there is one point outside the limit. And what is this point? Is number 11. If I want, I can go here and say remove number 11. Then OK, OK. And this is new set of limits, different from this one. As you can see, the center line used to be 0.095, now is 0.091. And the control limits are also different. The second type of attribute chart is the control chart focusing on monitoring number of nonconformities. For that, we have two charts, but we learn one more popular, which is C chart. Here is one example, or the of basically cases that we use C chart. The example is when we want to count the number of scratches on a surface, or we want to count the number of typos or the number of customer entered the hospital. Then in this case, we can use C chart. And as you know, the underlying distribution that we usually use for modeling this data is Poisson, and Poisson has one parameter lambda. Lambda is the average number of events in a unit. So this average in the quality control literature or language is called, is for example, scratches or defects, which is event. And the unit is basically usually the inspection unit, in this case, a surface of refrigerator. The mean and variance, which we usually use to construct the control chart, are equal, and both of them are lambda. Now, if I know this lambda, then I can easily find the control limit LCL and UCL. Now, C chart is used to monitor those Poisson random variables or defects, or the number of defects or number of events in a unit. As I said, there is a difference between nonconforming items and nonconformities. A product or a unit could have several nonconformities, but it may not be considered as nonconforming item. And that's why we do not use P chart in these cases. We use C chart, which is more on the application is on the side of using or counting the number of defects. So one term that we use in this C chart is inspection unit. An inspection unit is the number of units that we inspect and for counting the number of defects. And it could be more than one product. Okay, for example, in this case, if we are interested in finding the number of typos in pages, typed pages, we can define inspection unit as 2 pages. And basically, the total number of defects in this example is this plus this one. As I said, inspection unit could be more than one product or part. Why do we need to do that? Because in some cases, the average or lambda value is small. And we know that for short control chart, the main assumption is normality assumption. And for Poisson process to be normal, lambda should be large. And how we can increase the number of defects? So by increasing the number of, by changing the definition of inspection unit. So for example, if the lambda for average number of defects in one page is 5, then in 2 pages, on average, we have 10 defects. and lambda should be greater than 9, so we can use basically Schwartz control chart. So if we define the inspection unit one page, then lambda is a small and we cannot use Schwartz chart because the number of defects are not going to be normally distributed. However, if we change it to 2 or 3 pages, then we can use the normal approximation and therefore Schwartz control chart. That's the reason that we use basically inspection unit. C chart basically tries to monitor the total number of nonconformities in this inspection unit. Now, how we can construct a C chart, as I said, the total number of nonconformities in one inspection unit follows a Poisson distribution. And let's say instead of lambda, we are using C, which is the average number of defects produced in the process in one inspection unit. The mean and variance are the same. Therefore, if the C value or mean and variance is known, what we can do, we can easily find the control limits by using the Schwartz equations. So our CL would be C0, which is the average. UCL would be average plus 3 or K standard deviation, and LCL would be C0 minus 3 standard deviation. Now, what if we don't know that C value? So we collect data, we estimate C, which is estimated by this equation, which is the average number of defects divided by total number of samples that we have. And when we have C bar, we can easily find CL, LCL, and UCL. When a point is on a control limit, then it's considered as out of control point. Here is one example. We have 26 successive samples of 100 board. The inspection unit in this example is 100 board, so that 100 board is one inspection unit. Here is the number of nonconformities in one inspection unit, which means at time 1, we go and collect 100 boards, and we count the number of nonconformities, which is 21. The total number is 21. Second one, another 100 board is 24, and so on and so forth. So what should we do? Find C bar, which is the average of all these numbers, total number of nonconformities divided by the inspection unit that inspected. So that C bar is used to find the control limits. So that's LCL and UCL using the C bar that we estimated in the previous slide. And we can see that there are 2 points outside the limit. We have one bad, basically assignable cause, and one good assignable cause. The bad assignable cause is temperature control. We find the root cause, and we try to remove the assignable cause using corrective actions, by some corrective actions. However, this good assignable cause, we need to basically make it permanent. But we figured out that it's because of the inspection error. So the actual value should be greater than that. So we just train the appraiser, and we make sure that this doesn't happen. We remove these 2 points and we recalculate C bar. Now instead of 26, we have 24. And then this is the new C bar. Based on that, we have UCL and LCL. And based on this UCL and LCL, we will see that there is no other point out of control. Then we move to phase 2. And for phase 2 is one sample at a time. So sample 27, 100 boards, 16 out of the limit, and we plot that 16 on the chart, which is this guy. And then next sample, and as you can see, the process is in control, and we continue monitoring the process. Now let's see how we can use Minitab to construct C control chart. Here is one example. We have the example of the board, the PVC inspection. We have the numbers here. Phase 1, we go to a stat, control charts, attribute charts, and we select C chart. Where is the variable? It's here, and then we push OK button. So as you can see, we have 2 points outside the limit. We need to find the root cause, do the corrective action, and then remove those points. We go to estimate, and we basically first need to figure out what those points are. There are 6 and 20. Then we go to estimate, and we say 6 and 20 should be removed from the calculation. Push OK, OK. Then we have new sets of control limits, and based on this new set of control limits, everything is fine. Everything else is, or all the points are in control, so we can move to the second phase. So with this, we finish our lesson on attribute control charts. In the next lesson, we learn about EWMA and Q-sum chart and how we can use it for process monitoring. Thank you.